Hello, and welcome to our next section in Unit 4. We're going to continue our discussion about solutions and reactions, chemical reactions in solutions, and we're going to introduce some different kinds of equations. And there are basically three types of equations that we can use to describe reactions in solutions. The molecular equation, that's the one that we're all familiar with and we've been using for a while. We're going to also look at a complete ionic equation and a net ionic equation. So these three are different types of equations that we can use to describe reactions in solutions. So let's look at these. The molecular equation, as we've just said, shows the overall reaction. And the complete formulas, I know there's a typo, for reactants and products, but not necessarily what occurs in the solution on a molecular level. This is the equation you're familiar with. If we take our example that we just talked about in the last section, the potassium chromate and the barium nitrate, aqueous, those are in water, dissolved in water, producing the barium chromate, solid, and the two molecules of potassium nitrate. This one you're familiar with. This one is balanced, and we probably don't need to say much more about that. Some equations that you have not seen. Complete ionic equations. That is where we are representing all of the reactants and products that are strong electrolytes, and we're showing them as ions. All of the reactants and products are included in the complete ionic equation. So if we look at our molecular equation with this same reaction, and we rewrite it as a complete ionic equation, we're simply going to take it apart in its respective ions because they are all strong electrolytes and they will all dissolve in water and dissociate and float around as individual ions, right? So potassium ion, we have a K plus ion and there are two of them. So we need to write 2 in the front of the potassium ion. The potassium ions all go about in the solution. They travel around as individual K plus ions. There are 2 of them, so we write a 2 in front because we will have 2 K plus ions floating about in the solution. Here's our chromate ion, and as we see from our molecular equation, there's only one of those. We have barium ions. Those are have a +2 charge. We have one of those. We have nitrate ion right here, and there are 2 of them. They will completely dissociate into 2 separate nitrate ions, so we will write a 2 in front as a coefficient. The barium chromate will remain as a solid. It is not dissociating in that solution, so it will remain in this form. But we do have potassium ions, and there are 2 of them, so we will write it like this. And we have nitrate ion right here, 2 of them, so we'll write that like this. And there is our complete ionic equation. Now, what is a net ionic equation? We look at the complete ionic equation, and we're going to only include those components that undergo a change. All right? Spectator ions, they're just sitting back, like kind of like what you do when you watch a football game and you're not playing. You're just a spectator. They're not participating directly in that reaction, and we do not include those in the net ionic equation. We're only going to include those that undergo a change. That would be chromate and barium. So we'll take the chromate and the barium. Those react and form barium chromate solid. And this would be our net ionic equation. Now, let's do an example together. Write all 3 of these equations for the following reaction. If we take aqueous silver nitrate, add it to aqueous sodium chromate, and form solid silver chromate and aqueous sodium nitrate, what are those 3 reactions going to look like? So let's start with our molecular equation. Silver nitrate we have right here, and technically it would be silver 1 nitrate. If it's not indicated, silver is usually a +1. And then we have sodium chromate right here, and we're writing these down correctly, and then we're according to the names, and we can also write down the silver solid silver chromate right here, and the sodium nitrate. Those are the products formed. So I need to write all those down, then balance it. I can balance that by adding the coefficients of 2 in front of these compounds, and make sure I include aqueous, solid, and aqueous. Those are the states that all of my different compounds are in. And there I have my molecular equation. If I want to write the complete ionic equation, I'm going to take that apart. You can pause the video and look at this if you need a little more time to understand it, but my ions are all going to dissociate nicely into strong electrolytes. I'm going to have silver ion with a +1. There are 2 of them. And my nitrate ion, there will be 2 of those. Sodium ion is going to dissolve into sodium plus. There are going to be 2 of those. And my chromate ion, there's just 1 of those. Again, I do the same thing on this side. Although my solid, it does not dissociate into ions. Remember, it's sitting probably on the bottom of my beaker. It has probably traveled to the bottom because it's more dense than the solution that is around it. And it's a solid, so I leave that alone. And that's not dissolving or dissociating into the water. But I have my sodium ions and my nitrate ions. Now, for my net ionic equation, I am only going to look at those parts of the complete ionic equation that are undergoing a change. Okay, so that net ionic equation involves silver, chromate ions, and the silver chromate solid. So now you get to try this on your own. Here are 2 problems. Try these, see what you come up with. If you can get, write down all 3 of these equations. Write down the molecular equation, the complete ionic equation, and the net ionic equation for both of these reactions, and see what you can come up with. You will need to look in your textbook for the answers. They are on page 226. And if you need more practice, after you do these, you're still not comfortable, try the self-check exercises on page 226. All right, now that you are proficient in writing down the 3 different kinds of chemical equations, let's move on and talk a little bit more about some different driving forces in chemical reactions. We've already thoroughly looked at the formation of solids, precipitation reactions. Let's look at the formation of water. That's a driving force in chemical reactions, and anytime we have a reaction between a strong acid and a strong base, water is formed. So let's first take a look at acids. Strong acids completely dissociate or ionize in water. Here's an example, hydrochloric acid. If it is a strong acid, and a strong acid will completely dissociate, meaning that for the most part, nearly all of these chloride ions and hydrogen ions will dissociate in water and float around independently. Here's an example. A strong acid will look like this, where the different ions will completely dissociate and will move about independently in that water. A weak acid will not. Some of the ions remain attached and bonded in that water. So that's the difference between strong and weak acids. Acids, just as a side note, have been known about for a very long time. As a matter of fact, the word acid comes from the Latin word acidus, which means sour. So acids have been known about for a very long time. Some common strong acids are hydrochloric acid, nitric acid, and sulfuric acid. Nitric acid and sulfuric acid, back in the 1300s, used to be called mineral acids because they were originally obtained by treating minerals. That's how they were able to obtain those acids. So now what happens when we mix acids and bases together? We already said, we know, we form water. So let's take a little bit of a look at bases now. A strong base, just like a strong acid completely ionizes in water, a strong base completely dissociates or ionizes in water also. And here's an example. We have sodium hydroxide, and it dissociates into 2 ions, the sodium and the hydroxide ions. And those for the most part, sodium hydroxide almost completely dissociates or ionizes in the water. It is a strong base. Another example of a strong base is potassium hydroxide. Now, let's look at the neutralization reaction. Okay, that would be the reaction where we're forming water. And when we take all of these ions in our beaker, the hydroxide ion from the base and the hydrogen ion from the acid are going to combine to form H2O, which is water. We can write these equations down. Here's our molecular equation. Here's our complete ionic equation. And here's our net ionic equation. That is where we have the hydrogen ion, the hydroxide ion, and the formation of water. So let's just review. For the reaction of a strong acid and a strong base, we have some things that are always true. The net ionic equation is always the same, right? Because we always have hydrogen ions, hydroxide ions forming water when we have a strong acid and a strong base being combined together. So this will always remain the same. In this type of reaction, one product will always be water. So that's given. One product, the other product, will always be an ionic compound. Remember, we call that a salt. It will remain dissolved in the water. So you get to try one now. Write the molecular, complete ionic, and net ionic equations for the following reaction: aqueous nitric acid and aqueous potassium hydroxide. Go ahead and pause the video, try those equations, and look on pages 228 to 229 to verify that you got the right answer. Now that you are proficient at all these things, we have, you're able to write the three different types of chemical equations. You know about precipitation reactions forming a solid. You know about the formation of water with strong acids and strong bases. Let's take a look at this driving force, the transfer of electrons. And before we get into that, we're not going to cover the formation of a gas in a specific section. We will be referring to that in some later sections as a driving force, but for right now, these three are going to form a solid foundation for some different kinds of reactions. Let's look at this transfer of electrons. We know a reaction that involves the transfer of electrons, we are going to call that an oxidation-reduction reaction. And we're really going to just introduce that here on a very simple level. We'll talk more about that in our next unit in depth. But for right now, we're going to look at reactions that involve the transfer of electrons, oxidation-reduction reactions, and we'll just start with a really simple one, sodium chloride. We know that metals tend to transfer electrons to nonmetals. So here we have our metal and our nonmetal. We have a transfer of electrons happening. Sodium starts out with 11 protons, 11 electrons. It loses one of those so that it only has 10 electrons, so it becomes positively charged, whereas the chlorine has 17 protons, 17 electrons, and it gains that electron to have 18 electrons, so it becomes a -1 charge. So the first thing we want to look at when we are looking at an oxidation-reduction reaction is how are electrons gained and how are they lost in the reaction. In this example right here, well, let's ask that question. We are starting with reactants that are uncharged atoms, right? We have aluminum atoms and iodine atoms, and they are not charged, okay? But in the product, right here, we do have ions present. We have a +3 charge on our aluminum, and we know that because aluminum has a +3 charge. We also have -1 charges on each of those iodine ions. And therefore, Each aluminum atom from here loses 3 electrons because it's going from a 0 charge from aluminum in our aluminum solid atoms here, it's neutral, 0 plus 0, to a plus 3 charge over here. So each aluminum is losing 3 electrons, right? Now iodine, on the other hand, we are starting with a 0 charge, and each iodine will be gaining an electron to have a negative 1 charge. So each iodine atom gains 1 electron. So that is the answer. Each aluminum atom loses 3 electrons. Each iodine atom gains 1 electron. You try it. Look at this reaction. How are the electrons gained and lost in this oxidation reduction reaction? So pause the video and do that, and I will give you the answer on the next page. So here's your answer, and hopefully you got that right. And you can do some more practice problems if you need to. Ask me in class, and I'll find some of those for you. Now, let's review. That's really our main point with oxidation reduction reactions, is that it's a transfer of electrons. It's a driving force in chemical reactions. When can we count on oxidation reduction reactions happening? When we have a metal and a non-metal reaction, we always have an oxidation reduction reaction, metal to non-metal, because there's always a transfer of electrons. When we have non-metal interactions, sometimes there is an oxidation reaction that occurs. And we will discuss this more in a later unit, but for right now, you know that if you are starting with elemental substances, or you're ending with elemental substances, you are probably going to see an oxidation reduction reaction, as in this case. The oxygen here is a neutral charge. It's just elemental oxygen. And in the products, however, it is forming bonds with other nonmetals, and it is going to be exhibiting charge within those. So when we have non-metal interactions, and we are starting with or ending with elements, those probably will be oxidation reduction reactions, because there will be some kind of electron transfer involved. Advanced ideas. Learn more about redox reactions. Oxidation reduction reactions are often called redox, for reduction, oxidation. Learn about oxidation states. Learn more about acid-base reactions, pH, calculating it, buffer solutions, etc. And I look forward to seeing you in class.